Last section, we looked at how do you solve a system of equations graphically. Essentially, you would use Desmos, you would draw the two graphs, and if they intersected, which you hope they do, you would find a solution. If they were parallel, you would say there was no solution. And if you had one line on top of the other, you would have essentially an infinite number of solutions. So what we're going to look at now is how to solve a system of equations using a purely algebraic method called the addition method. So let me start off with a very simple example of how that might work. So the equations that we're going to deal with are going to be when the two equations are written in their standard form. So that means so many x's plus or minus so many y's equals a number. And in this case, we'll have that. I'm going to call this equation 1 for simplicity, and I'll call this equation 2. Essentially, what the addition method says is that if you can arrange to have these two equations in a very special form, then what you can do is you add the two equations together and you will be able to eliminate one of the variables, either the x's or the y's. It really doesn't matter which, as long as you can eliminate one. Now this one is ready to go. So that particular shape you're looking for is you want one of the equations, in this case y, to have a positive number of y's and the other equation to have the exact same amount but a negative. The result is that when you add these two equations together, which is why it's called the addition method, something really quite cool happens. If you add these two equations together, you get 5x. Here's the tricky part, the nice part. If you add these two together, they cancel each other out, and so you get 0. And then if you add these two together, you get 25. So what you've essentially done is by adding these two equations together, you've eliminated the variable y, and now you have a very simple equation where all you need to do is solve, in this case, solve for x. So I'll divide both sides by 5, and we are halfway there. We have x. We now know that x is 5. So all I need to do to finish this is find out what the corresponding value for y would be to make this work. So it doesn't really matter which one you choose because you're going to end up with the same value for y. So I'm going to put x equals 5 into equation 1. So I'll write equation 1 down. It says that 2x plus 3y equals 10. So that's 2 lots of 5 because x is 5. Add 3y is 10. That gets me 10 plus 3y equals 10. Kind of cool. Now, I have an equation with one unknown, a linear equation. I'll subtract, in this case, 10 from both sides. And then I'll divide both sides by 3. And now I have the corresponding y value. So in this particular question, the solution, which in WebAssign would almost always be written something like xy equals, and then they'd give you, a bracket like this, and we'll get like that. And you would put x is 5, comma, y is 0. And that's how you would write it down in WebAssign. And that's probably going to be the simplest situation that you're going to come across. What's more realistic and more likely to happen is that the two equations that you get at the start won't be in a format that is going to lend itself to just adding the equations directly together. So suppose we get, as an example, let's see, pick one. Suppose we have 2x plus y is 4. And 3x plus 2y was 7. And I'll call this equation 1, and I'll call this one equation 2. Now, when you look at this equation, it's pretty clear that if you add them together, nothing cancels out. These become 5x and these become 3x. And so we have to adapt. And the way that we're going to adapt is, I'm going to decide whether to get rid of the x variable or the y. And it looks to me like the simplest one to get rid of would be the y. But to do that, I need to change it from plus 1y to the opposite of this, which is negative 2y. And so the way that you do that is that you multiply this equation by negative 2. So let's see what the new equation looks like. Everybody here gets multiplied by negative 2. So that's negative 4x, negative 2y equals negative 8. And then underneath that, I'll write the second equation untouched. So I'm now going to call that my new equation 1 and my new, my same equation 2. Now, when I have this form, do you see that we've now got it in the shape that we're looking for? The same number, one is plus and one is minus of y's. Once you can get that, you then can move on to the add each equation. So if you add these together, you get negative x. If you add these together, they cancel out. And if you add these together, you get negative 1. And so what I'm left with is a very simple equation, only involving x's. In this particular case, I guess I could multiply both sides by negative 1, and we have our first solution. We are halfway done. I know that x equals 1 will work. And then you take that and you put x equals 1, and you choose any equation you like. You can choose this, the old version of 1, this one, the new version of 1, or version 2. No particular reason, let's pick this one. So I'm going to put it into 3x, add 2y equals 7. So that's 3 lots of 1, add 2y equals 7. That's 3 add 2y equals 7. Then we'll continue to solve for y. So I'm going to use that method I give the nickname, as long as you do it to both sides, it's okay rule. So I'm going to subtract 3 from both sides. I'm going to divide both sides by 2. And we now have our solution. Our solution is that xy is 1, 2. And if you go to the equations that we were given at the start, if you plug in 2 here, 1 here, you plug in 2 here, what do you get? 2 times 1 plus 2. Yep, that adds up to 4. Does 3 times 1 plus 2 times 2 get you 7? Yes, it does. This one's a bit messy, but it works. If you do negative 4 times 1, negative 2 times 2, does it get you negative 8? Yes, it does. This is the unique and only combination of x and y that all these original 2 system of equations will work for. None of the others, there are no other combinations. So let's try what looks, I guess, as a relatively simple situation and see what we got now to see where we go. There's my first equation, and here's my second. Now we are looking at 2 equations, right? A system of equations. We're trying to solve, if it's possible to do so, by finding an x and y that make both these equations work. Now I'm looking at the patterns of the x's and the y's, and I can see straight away that they're not ready yet. There's 8 of these and -5 of them. That's not going to work. There's 1 of these, but there's still 1 of these. I don't want 1 and 1. I need 2 and -2, right? I need 1 to be positive and 1 to be negative. Because of that, that tells me that I probably should multiply either this equation by -1 or that equation by -1. It really doesn't matter which one I choose. So I'm going to multiply the first one by -1. So -1 times this guy, -1 times this guy, equals -1 times this guy. So that's my new equation 1. Equation 2, I don't need to do anything to that one, so I'll just rewrite it. And there's my equation 2. We've got the pattern we're looking for, right? Same number of x's, but one's positive and the other, the one above it, is negative. We can now use the addition method. If you add these together, -x add x, they cancel each other out. 5y add 8y gets you 13y. And -6 add -7 gets me -13. And now I have an equation with only one variable, in this case y. So I'll divide both sides by 13, and I have half my solution, halfway there. I'll then put the y equals -1 into the old equation 1 or the new equation 1 or the equation 2. I have no real interest in which one because they all work. So I'll pick that one. And that becomes 8 lots of -1 equals -7. So x take away 8 is -7. So far, so good, I hope. Right, so what I'll do next is add 8 to both sides. And there we are. We've got our solution. And our solution is that the combination of x and y, the only unique one that works, is x is -1 and y is -1. And we can basically call it done. Okay, let's look at another situation. This is a version of question 3. In this case, we have x take away 3y equals -4, so I'll call it equation 1. And we have -3x add 9y equals 12. Now, before we continue to solve this, let me remind you the 3 situations graphically, what can happen. The 2 of them cross, in which case you get a unique answer. The 2 equations end up being parallel lines, in which case you would just say that they're inconsistent. And then the most awkward one, which I know this is what this is going to happen, that the first line, which is the top one, and the second line end up being the same line. And in that case, we have a little bit more extra work because the way we set out the solution, it involves a little bit more detail. Well, I'm looking at these equations and I'm looking at, have they got the right format? Well, there's a negative and a positive x, that's good, but this is -3 and that's not anything. So I'm just going to multiply the first one by 3 because I've decided to get rid of the x's. So 3 times x, 3 times that guy, 3 times that guy. And then that's my new equation 1. My equation 2 is -3x add 9y equals 12. So these are in the right format, but something really weird happens. The x's cancel out. The y's cancel out, so that means 0 is left. And you add these 2 together, and it's also 0. And that when this happens, right, when all the x's disappear, all the y's disappear, and all the numbers disappear, and all you're left with is zeros and zeros, you are looking at two identical lines. So essentially, there's an infinite number of solutions. So what you do here is you pick any equation you like. So I'm going to pick equation 1, which is that guy. Hold on a moment. Okay. Here we go. And I am going to solve this equation. I am going to, by that I mean I'm going to rewrite it as y equals. So I'm going to subtract an x from both sides. I'm then going to divide everybody by -3. Negative 1x divided by -3 gets you positive 1/3. -4 divided by -3 gets you positive 4/3. And our solution, the one that you will write down in WebAssign, won't be number comma number. It will be x, always x, that guy. And when you write that down, you're basically saying that the solution is any point on that line, because all the points on that line work. So that is an example of the third situation, right? Both lines are the same. Let's see if we can find an example then where this happens, just to show you what the math looks like. So a version of that would be question 5. So this is pretty rare, right? You don't expect this to happen often, but it will happen from time to time. Inconsistent, which is the parallel line situation, which I'm about to do, that happens pretty rarely as well, right? The most likely event is going to be a solution that you can calculate two numbers with, an x and a y value. Right, let's return back to this one. We have a 6x plus a 9y equals 6 for that equation 1. And we have a 4x plus a 6y equals 5. Now, this is probably one of the more, it's the most difficult situation to cope with, because what you really have to do here is you have to change two equations. You have to change equation 1 and equation 2, because remember, what our goal is to have the same number of x's, but 1 plus and 1 minus, or the same number of y's, 1 plus or 1 minus. Doesn't matter which one you go for, that's what your goal is. As I say, it doesn't matter which one you go for. If the solution is a pair of numbers, that's the solution you'll get, no matter which one you do. If it's one of these situations, that will also happen. So since it doesn't matter, for no particular reason, I'm going to get rid of the x's. And that's where the problem lies. There's 6 of these and there's 4 of these. So I know that I have to change both of them, and I'm trying to avoid that, multiply one of them by a really awkward decimal, which I don't want to do, or awkward fraction. So I'm going to multiply this equation by -4, and I'm going to multiply this equation by 6. And that just means multiply. Now you may say, where did those numbers come from? Why have I chosen those two and, not some other number? Well, if you multiply this by 4, you get 24. And if you multiply this by 6, you get 24. Do you see, if you just choose the opposite coefficient, that's the easiest way of getting around this problem. So the new equation 1 becomes -24x, -36y, and it's going to equal -24. And that's my new equation 1. My new equation 2, right, you multiply everybody by 6, and you'll get 24x plus 36y and plus 30. And we will add the equations now. And when you add these, they disappear. When you add these, they disappear. So you get 0. When we add these, however, you get 6. Now, we've got to understand that when something that is obviously not true happens, right, that's 0 is never going to be 6, that it has to be interpreted in terms of the three possible situations. When the two numbers, when the two things both disappear, right, 0 on the left, 0 on the right, we're getting this guy. When all the variables disappear, but there's a number here that's not 0, right, in this case 6, this is inconsistent. Essentially, if you sketch them, you would get two parallel lines. And so our solution in this case is we write down the word inconsistent. I guess you could say that meant there are no solutions. Nothing, no combination of X and Y, no matter how weird they may be, would ever work. Okay, so let's try another question where we have to change both of them. So the one I'm going to do this time is going to be question 7, or at least a version of it. So 4x, take away 5y is going to be 17. And 5x, add 3y is going to be 12. And I'm going to call this equation 1 and equation 2. And it's pretty obvious that they're not matching. That's 4 and that's 5, and they're both positive. That's at least got a negative and that has a positive. That's good, but the numbers don't match. And this is a situation where I cannot multiply 5 by anything to get 3. And there's no way I can multiply 3 by anything to get 5. So I know I'm working on changing both. So I'm going to multiply this guy by 3 and this guy by 5. And you see what happened? Multiply it by 3 and 5, and y chose 3 and y chose 5. So everybody here gets multiplied by 3, so that's 12x. Take away 15y, 3 times that fell out is 51. There's their new equation 1. Multiply all these guys by 5, and 5 times that gets you 25x. 5 times that gets you what I was hoping for, plus 15y. And 5 times this guy gets you 60. And that's our new equation 2. Put a little separation line here. Now, in this format, we've got the same number of y's, but 1 plus and 1 minus. Once you can get that shape, you can now add these together. You get 37x. These two get you 0, right? They cancel each other out. And these guys get you 1, 1, 1. And then I would divide both sides by 37. And I'm hoping that that comes out as a nice number, which I'm pretty sure it will. 111 divided by 37. And yeah, you get 3. So we have half the answer. We know that x equals 3. So what we do to finish is we put x equals 3 into any equation that you like. I like this one. Not really, but I'm picking it. So 4x, take away 5y is 17. So that's going to be 4 lots of 3, take away 5y is 17. That's going to be 12, take away 5y is 17. If you subtract 12 from both sides, you get that. And if you divide both sides by -5, you get that. And here we have the typical type of situation that you get where there's actually one solution. So our solution, the x and the y, will be 3 and -1. Okay. Now, let's make things a little bit weirder. What should I do to be weird? Oh yeah, let's make the equations much uglier than you would want. So this is a version of question 10, and we're going to deal with a system of equations where the coefficients of x and y, that's 3, are fractions. So there's equation 1. Well, if ever you give me a system of equations where the coefficients of x and y in particular are fractions, I am not going to let that stand. I am going to try right away to get rid of the fractions. So what I'm doing here is I'm going to find a number that gets rid of quarters, gets rid of thirds, and gets rid of halves. And the number that's going to do that is 12. And I want to get rid of halves, sixes, sixths, and halves. And the one that does that is 6. So basically, find a number that's in the 2, 3, and 4 times table. And once you get a number that's in the 2, the 3, and 4 times table, in this case 12, that's the guy you should work with. In this one here, find all the numbers in the 2 times table. Well, this is dead easy, right? 6 times 1 is 6. It's in that table. And isn't 2 times 3 6? It's in that table. That's why I chose 6. Right, in this case, I always pick the biggest number. 4 times 1 is 4. Nah, it's not in those 2 tables. 4 times 2 is 8. Still not in those tables. 4 times 3 is 12. Yep, it's in the 4 times table. Is 12 in the 3 times table? 3, 6, 9, 12. Yep. Is 12 in the 2 times table? Yep. That's why this is 12 and why that is 6. So this line that we're doing is only got one job. It's to make all the fractions go away. So 12 times a quarter gets me 3x. 12 times that guy gets me 8y. And 12 times that guy gets me, I believe, 18. And there's my new equation 1. Multiply everybody here by 6. And I get 3x, multiply this by 6, you get negative 5y, and multiply this by 6, and you get negative 21, and that's my new equation 2. Put a little separation line there. Now, I hope you would agree that these equations were much easier to deal with than these ones. So pretend that these never existed and focus on solving this system of equations, because this solution will be the same as that. Well, I'm looking at the x's because I think they're the candidate that requires the least amount of work. At least they're both 3. Problem is one's plus and so is the other. But I can fix that by multiplying this fella by negative 1. And so I now have negative 3x, negative 8y equals negative 18. And that's my new equation 1. And I have 3x take away 5y equals negative 21, and that's my new equation 2. And we have got the balance here, right? The x's are the same, 1 plus and 1 minus. If you combine them, add them together, they go away. These two get you negative 13y, and these two get you negative 39. So we now have an equation involving only one variable, y. Divide both sides by negative 13 and you get a really nice answer. It ends up being 3 for y. So here's half our solution. And now I'm going to put y equals 3 into any equation I like. I could put it into that one, but God forbid I even thought that was a good idea, because I never would. I could put it into that one, which is even worse looking than that. But I could put it into this equation and it would work, and that's not too bad. Or even this one. I like this one, so I'm doing it. So I'm going to put it into 3x add 8y is 18. That's going to be 3x plus 8 lots of 3 or 18. 3x plus 24 is 18. Subtract 24 from both sides, and then divide both sides by 3. And we have got the corresponding value of x. So we have our solution. We are looking at x and y has to be negative 2, 3. Finished. Kind of cool. Just trying to get my camera a little bit better adjusted. Okay. Well, we've done quite a few. That's question 10. If you do question 11, it's very like question 10, right? You've got some fractions to deal with, and that's not unusual. Let's look at a different problem. This is a version of question 12. So what they're doing is they're just putting in an extra complication. So that says 2x take away 2y, and it's going to equal 5x minus 1. I'll call it equation 1. And then I have 2x plus 7y equals 4y add 9, and that's equation 2. And your temptation might be to just work on the equation the way it is. But the thing I've noticed is that there are x's and y's in the right-hand side. They shouldn't be there. Only numbers should be there. So what I'm going to do is I'm going to subtract 5x from both sides. So that now becomes negative 3x, take away 2y is negative 1. That's a much nicer looking equation. I'm going to subtract 4y. If you subtract 4y from this, you get plus 3y equals 9. And that's now my new equation 2. So we are going to be solving that much more standard looking system of equations. And it looks to me like there's all sorts of interesting things that could be happening here. I could try and get rid of the x's, or I could try and get rid of the y's. I'm really 6 of one, half a dozen of the other. Let's get rid of the x's. Well, there's a negative 3, that's good, and there's a positive 2, that's good, but they're totally different values. They're 3 here and 2 here. So I'm just going to multiply this guy by 2 and this equation by 3. So the reason that's a 2 is because of this guy. The reason that's a 3 is because of this guy. So what do you get? You get negative 6x, negative 4y equals negative 2. That's the new equation 1. And multiply everybody here by 3, and you get 6x, add 9y, add 27. Now we have the same number of x's, but 1 plus and 1 minus. We are good to go with the addition method. Add the x's together, they cancel out, you don't get any of them. These two, combine them, you get 5y. These two, combine them, you get 25. One equation, one unknown. Divide both sides by 5. We are halfway done. I now know that x is 5. I'm going to put, I said x, y, I should say. We now are going to put y equals 5 into any equation you like. I don't really like these because they're kind of ugly, so I'm going to pick one of these two. I think I should pick that one. So 2x add 3y equals 9. That just seems to me to be the least amount of work. So 2x plus 3 lots of 5 is 9. 2x plus 15 should be 9. Subtract 15 from both sides. Divide everybody by 2. And we now have the corresponding value of x. So we have a unique solution. And that solution says that you only need to pick x as negative 3 and y is 5, and it will solve this system of equations. And you could plug in x is negative 3 and 5 in here, and x is 3 here, and this would watch, right? The left and right hand would end up being the same number. You could do it to equation 2, and I guarantee it would also work. So we are good. And that is us. So hopefully that has been some help, and I'll have this online as soon as I can. Bye for now.